Okay, welcome to our structural modeling project video conference for June. And we're going to continue our discussion of relationships, structural modeling concepts. And in this particular episode, we're going to actually talk specifically about local and global relationship concepts. We've been working to organize and identify different components and parts of systems. Structural modeling is developed by Warfield. Reviewing some of his documents and some of his publications. And now in this specific document, we've focused down into the idea of the local and global relationship concepts. And what do those mean? Why are they important? What can they actually do for us? Why would we want to introduce these concepts, and how do they help us? So those are some of the things we're going to talk about today. And just a little bit of a discussion of what the upcoming meetings. I know we're going to have a meeting in 2 weeks, and I'm not sure who's going to take the lead on that one. So before this meeting's over, it'd be good for someone to indicate who has the lead for the content on the meeting 2 weeks from now. And then in the July meeting, next July, the first Saturday in July, what we're going to talk about is how these global and local relationships impact our computer algorithms and impact our approach. So we'll be now starting to go a little bit more into matching these relationship concepts and these types of mathematical structures that were developed by Warfield and expanded by Mary and I. And then we'll start mapping them more directly to executable types of computing algorithms. Is what will be is the direction we're going to start heading now. So is there any questions on that? Okay, so what we'll do then is I'll stop screen sharing here and bring up the read-ahead document for this month, which is local and global relationship concepts. And the local and global relationship concepts were established to talk about the common types of relationships we see in systems. And the examples that we use in this report were taken from the literature, from the interactive handbook, and also from the Science of Generic Design and some of the other publications by Warfield. So we'll look at the problematique, which is the problem structure. We'll look at the enhancement structure, the intent structure, and the curriculum structure and the priority structure. Now those were taken from the handbook of interactive management. And then these three types were standard examples will be combined with the 19 cities problem, is heavier than relationship, and is in the same category relationship. Well, we use these to actually give a detailed evaluation of global and local relationships. So a global relationship by some artifact, something that is available everywhere that we know about within the group, and that artifact is essentially used to help evaluate, rate, rank, or analyze the relationship between the objects in some way. And so the idea of the global gravity field, one thing is heavier than another, that's a relationship that's mediated by the gravity field, for example. A local relationship maps directly between two objects. And so when we say, like in the problem structure, problem A exacerbates or aggravates problem B, there's no intervening artifact between those two. It's just that problem 1 and problem 2 are acting on each other. So a local relationship really has no artifact that's intervening between the objects. And then the global relationship has a mediating artifact. So these are the concepts we're developing and going to be using to help focus on different types of efficient computational processes. Okay, and then of course the standard definitions that we use in this work. And so in our last technical report, we talked about some of the matrix-based application structural types. And these basically are these types of structural types and the relationships associated with them are listed here. And so that, as I mentioned earlier, the is heavier than relationship, the mediating artifact is the Earth's global gravitational field. And that's a physical representation. It's there. People have defined what it is. We've researched it and so forth. We know a lot about it. And so that is the controlling artifact there. The second example is north of. The mediating artifact is the relation in the relationship is the common global spatial orientation. This is kind of a conceptual global idea, but it's a conceptual map that people need to have to be able to understand the is north of relationship. So, and then the third example is in the same category as, and the mediating artifact here is a set of commonly understood category patterns. And this is important that people that are in the group that are doing the evaluation really need to have a fairly close common understanding of what these categories are and what the patterns are so that they can determine whether or not the objects they're evaluating fit the pattern, one pattern or the other. And then the fourth example, of course, is a priority structure, which has a relationship has priority over or has the same priority as. Now that's from the handbook, and we don't, in the systems concepts approach to structural modeling, we don't allow that has the same priority as, because we do a has priority over or is a higher priority than of priority classes. And if two things are the same priority and in the same priority class, and so we just use that approach. And of course, the mediating artifact is a collection of global priorities. But in this particular case, people are discussing and evaluating, and they're creating and communicating about their global, creating this global priority map probably as they are interacting. So it's a little bit different than a standard gravitational field. It's always available, but again, it's the same concept. There's something other than the objects themselves directly interacting that's used to create the relationship. So we said the gravity field is well known, and as we go from that to where we're talking about the priority structure, things like that, those then become less well known and they need to be discovered. And that's part of this process, that part of the methods and techniques that need to be evaluated. So really how much effort and what is the best way to make sure that that's actually happening. So these are things that need to be part of the structural modeling approach. So this is a more detailed evaluation of the is heavier than example. This is an example right out of the appendix in the Handbook of Interactive Management. It's one of the ones that's used to demonstrate the software technique in the back. And so we actually, this graphic here is a representation of the of our software that we use to reproduce the same effect that was published in the handbook. But it's essentially a global gravity field that we use to rank order these objects, which is heavier than the other. And there's a couple interesting things to think about here in this relationship and it being a global relationship. The first thing is it has an asymmetric logical property. The second thing is that there's a single thread in the structure. It's the way that the gravity field works and the way the weight works, the relationship, there's only a single thread developed among these objects. One thing is either heavier than something else or it's not. So there's no splitting or multiple paths through the structure. It's simply a single thread. And then the third thing to think about is that there's common activity and common analysis from the universe to the feather, all the way down to a single thread. You don't have to consider, well, is the universe is heavier than a Mack truck, but is the universe lighter than a feather? But you don't have to worry about the opposite in this particular concept, or the opposite effect. And for example, in a problem, if you say problem A exacerbates or aggravates problem B, and problem A exacerbates and problem B exacerbates problem C, you also need to check and make sure that problem A doesn't alleviate or make problem C better. And so in those cases where you have local interactions, you need to think about the uniform application over a space. In the global application here in this concept, you don't have to worry about that because of the nature of the concept. And that's not very well articulated yet, but it's something that I think needs to be developed, and we're going to have to create some terms so that we have a common understanding of that interaction. In the north of example, again, this is a fairly straightforward type of concept, and what we're doing, yet again, is we're looking at this and we're saying, well, there's a global understanding of a spatial relationship, and we're ordering them as north of. And we're just ordering the longitudinal category, so that even though that's city 8 and city 9 are at the same level, we are putting city 8 and city 9 in the same longitudinal category, and then we are ordering the longitudinal categories. So if they're at the same level, we then put them into a group and address their order as a group. All right.
Okay, I have a question about that graphic.
Sure.
So how do we make the determination that something is on the same level as something else? Like 8 and 9 are obviously on the same level, but 7 and 9 are slightly overlapping, but not on the same level. So how do we make the determination? But my question is, how do we encode how we make the decision? Is that the relationship itself, or is that in the context? What was that?
Yeah, so you want to know what is the discriminating metric in this case? For location?
That's not my question. My question is, how do we store? Do we do that in the relationship, or is that in the context of the modeling activity?
Yeah. Okay, so that's really a good question, Thomas. I think that there's a number of ways you could do this, and I think the metric that you choose to determine where a city is located, exactly at what latitude it's located, and exactly what the differentiation, how much difference do you need between two cities to say that they're same or different, right? So you need to say, oh, okay, what's the distinction? How much different do these things have to be before I say there's a difference? That's the first thing you need to do. Second thing you need to do is you need to determine the metric. How are you going to do that? So there's a number of ways you could do it. You could, for like, let's say a city that has a spatial area, you could do a moment of the center, a moment of the area of the city, pick that point and say, okay, that longitudinal point represents the city. Or you could say, well, no, I'm just going to use the most northern point in the city or the most southern point in the city. You know, those are operational things that you need to determine, but they need to be common throughout any specific activity and documented. That make sense?
That makes sense, but I don't think what I was trying to ask got through.
Okay, good. Try it again.
So the metric, the determination, is that part of the relationship, or is that determined within the context of the modeling activity that uses a relationship?
Right, so the relationship is, the metric itself, right, is not part of the relationship. The relationship, let's say, for example, where you're structuring a system and you're saying, okay, the system works, like we have it here, it says is north of. Is north of is the relationship. And there's no real metric that you can use at that level of abstraction, right? But when you go to apply it, because is north of and structuring the cities, the objects of the cities is very abstract. But now we're going to have a specific instance of applying this. We can say, okay, we're going to do this now, okay? And for you to implement that abstract thing in a concrete way, then you have to start making these decisions and documenting them so that everybody knows this is what you did and this and how it affected your outcome. Did that answer your question?
Yeah, I believe it did. Thank you.
Okay. All right. So, as Thomas pointed out here, what we're working with right now are fairly abstract concepts and ideas. And these abstract concepts and ideas, we're going to then attempt to translate to a class or one or more classes of algorithms. And then those algorithms basically will need the concrete data of a specific instance for them to be executed and to have meaningful representation in the real world. So there's a range of activities we're going through right now. But this one is we're just trying to identify this pattern between local and global, and that we've observed as we've been studying these examples from Moorfield and other literature. And we've noticed that the idea of a single thread, multiple thread, and this nature about the concept. And so we came up with these terms, global and local, to help us start categorizing in a general manner relationship types. And then once we have these relationship types better quantified, then what we'll be able to do, hopefully, is to start assigning the proper computing algorithms, or designing the proper computing algorithms with. Okay. So where were we here? Here we are. Okay, in the same category as example. So in this particular case, in the same category as is the relationship actually is symmetric, right? The other previous relationships that we were talking about were asymmetric. Now in the same category as is symmetric. These are equivalents. And we're doing pattern matching. And so we have a group of objects, and we have a group of patterns. And we're saying, okay, does this object fit this pattern? So the common set of patterns really has to be negotiated among the people. And it's not like like the gravity field, which affects all individuals. Everyone has experience with it, those types of things. What we have in this particular case now is kind of an abstract idea of patterns, common patterns that people need to understand those. I think in many cases, it's been in my experience, especially in large-scale technical systems, that the identification of the patterns and an agreement on what they mean is probably the most difficult step. And this starts with the overloading of the terms and words. Technical, a word will mean a very specific thing in one technical branch where it means something completely different in another technical branch. And so when you're bringing different groups of technical people together and experts, focusing them on a large-scale problem type of situation, they're using the same word to mean different things, and they don't realize that they're misunderstanding themselves. And so these are the types.
Page down.
These are the types of things that we really need to look at to understand how well do we need to define a category, and are there some tests? Are there some types of simple tests we can use to say, okay, people pretty much understand this to a level where we can go forward and do categorization. So those are all fairly straightforward concepts. Now, when we look at this symmetric global relationship, what we find here now, though, is that we have multiple threads, right? So we have one thread for each category or for each pattern. So if you have three kinds of things, three patterns. Oh, yours is not paging down? Okay. Oh, Peter, I lost my screen share. It's back now. Are we okay now?
Yes.
Yes.
Okay, good. All right. Yeah, it might be a little bit of a lag there. So in this particular case, I was saying that we have a symmetric relationship because they're the same as, or equivalence, which is reflexive, symmetric, and transitive. And each one of these patterns then will generate its own thread. And so there will be one structural thread for each pattern, identified pattern type. But again, this is global, so we have these global concepts, and everybody understands that there were then, and that's the mediating artifact that we use to structure the system. Okay, has priority over. So this again is another asymmetric relationship. And this asymmetric relationship is involved in another field that's really being determined almost simultaneously with the evaluation of the priority. So we have 20 or 30 people that gather together and they're going to evaluate a set of objectives and they're going to prioritize them. And those 20 or 30 people came together and they walked into the room. They didn't have a normalized set of objectives. So there wasn't like the idea of the categories or the patterns where you needed to normalize the pattern set before you started working on the creating the system structure. In this case, when you start working through the objectives and prioritizing them, you are using a very general idea of, global idea of ranking, rating, I guess you'd say sequencing, but that's a very general concept that's used to actually create the objective structure. So when we're looking at these types of global relationships, I think we can identify and further document classes or attributes for these different kinds of global relationships and what types of activities need to be focused on, maybe what the algorithms are, those types of things. So this is just a real general introduction, kind of a high-level overview, start the discussion of these things that we've noticed in the literature. And so that's kind of the initial part on the global. Now the local relationships, they operate directly between the objects of concern without the presence of a mediating artifact. And there's many excellent applications of this. The ones that we're going to talk about here where the local relationship is used is the problematique of the problem structure, the enhancement structure, the intent structure, and the curriculum structure. And so we have, again, another challenging situation where one individuals participating in the process need to share a common understanding of the relationship semantics. This activity and this really the fundamental initial condition that you have to have is have to have some shared context among the people in the group before you can really make much progress. It's usually in these areas, the individuals will be like from a large industrial organization or a political organization, or some type of shared organizational or interaction structure that makes these people understand that they may have common problems and they want to define what they are and see if they can bring some solution to those problems. Right? And so those are things that really, it's the first step you need to decide is how do we establish common context? And the structural modeling process may be one way, one structured way to start establishing this common context. What you may find is when you do that, that there's really not enough common context among the participants to have an effective structural modeling event or activity. So these things within the local relationships now, they really depend much more on the understanding and
We've lost.
everybody there still?
Joe's back.
Okay. All right. Well, let's see if I can share my screen again. Having some interesting. All right, does everybody see this local relationship screen there?
Not quite yet.
No, don't see it.
Okay. All right.
It's still not there.
Still not there. Okay. Huh. That's interesting. Well, the internet, this must be slow today. But everyone I think has a copy of this. I sent it out, so I'll kind of work through it a little bit more. So each one of these structural examples represents a unique type of system. And again, in many cases, this identification of the problematique and this type of structural modeling may be the first structured activity that's going to be used to for developing context among the group. And we want to evaluate methods and steps that can be used to do that. Okay.
Because the
Hello?
paper is not up, refer to page 6 and then going into 7 was where you're talking now.
Yeah, that's right. Page 6 going into 7. I'm on page 7 now, all right? Exactly. And so in the problematique, the system logics are structured, are problems, and the natural language relationship is aggravates. And so, again, we talk about the non-alignment of these particular activities because of the problem is an active dynamic behavior, aggravates is the active behavior, and we're really doing structural modeling. So it's kind of a little bit of non-alignment there between the modeling technique and the system dynamic types. We talked about this in more detail in Technical Report 7 last month. And so what we need to do is actually need to think about a little bit more about these behavior types and whether or not they're stable enough to be used for a modeling case. And then also whether or not they are they propagate. Not enough really for them to be transitive, but I mean essentially is make sure that the problem aggravates, creates a system where that transitive behavior is goes along all of the problems involved. Now, when you think about, well, what if I have a problem here that aggravates 3 of these problems, but it alleviates problem number 5. So that evaluation, you can just assume that that's never happens, or you can go through and develop some kind of technique to make sure that, to evaluate that and get some information about it. In the local relationship, when you do that, it seems to kind of work against the efficiency of the structural modeling process. So in the structural modeling process, for it to be efficient, you're assuming that that doesn't happen. And you don't have to go through and check that, because if you did that, you'd have to do it for, for each object against all the other objects in the network. And that is a very computationally intensive and also a labor-intensive type of activity. So mention it here because it needs to be thought about. If you decide to go that way, much of the efficiency of the structural modeling process will be lost. So what we will probably want to do is find natural language relationships and concepts and techniques where we don't have to do that, where we can then take advantage of the efficiencies of the logical structure. Okay, so then the proper application of logical relationship requires that the structural process be controlled and verified. It's clear that the relationship operates between two objects without a mediating artifact. So that definitely makes it a local type of relationship. Okay, I can see that I think you have page 7 up now. And I'm moving on.
That's correct.
Yeah, moving on down the page to the enhancement structure. Okay. Moving on my screen, but I don't see it moving on the other broadcast screen.
The enhancement structure is up.
Oh, okay, good. So the enhancement structure example is similar to the problematique, except of the difference between the objects and the natural language relationship. The fact that what we want to do in the enhancement structure where the objects are action options, things we can actually do, and we want to enhance the value of other action options. And if you have a situation where you've just identified the problem structure, and that's kind of set the context for the individuals involved in that process, and then you switch over and say, okay, now let's go and look at an enhancement structure. There's not a direct relationship between like the problems and the enhancement, the problematique, the problem structure and the enhancement structure, except that the people themselves and the activity themselves are carrying the memory in a common context. It's not like, oh, I have this set of problems and now I'm going to have this set of solutions we're going to look at. So it's kind of an intermediate step. And people now start thinking about, well, how can or what type of activities and actions can we take that will actually make things better, will enhance the value of whatever your value structure is. So this is needs, again, to be a positive additive nature of the enhancement. You don't want any of these actions to decrease the value of any other. Basically, if you can just assume that, but if you decide to go through and check it, then that's going to, again, greatly increase the effort it takes to check each one that there's no negative impact. So that might be a risk type of factor that could be addressed by identifying techniques, relationships, and processes that sidestep the idea of having a negative side to them. And of course, the enhancement structure is, again, the local relationship because it operates between the two objects without a mediating artifact. The intent structure, it, again, is like the basic structural form and attributes of the problematique, except the objects are goals, intents, and aims, and the other one is supports attainment of. So as you can see, once you identified your problems, looked at those as a group, and if you go through and you look at an enhancement structure or ways that you can enhance and make things better, right? And then you can look at an intent structure. So these are not directly aligned with each other, but if you have a group of people where you're using these techniques to increase the shared context and the common information and understanding among the group, then it's creating a situation where you may be able later on to come up with better solutions using different types of techniques or other structural modeling or other types of system modeling techniques and approaches. So again, the additive nature of the relationship ensures the propagation and the impact. So we're always going to want to make sure that it supports the attainment of all of the objects, that it just doesn't support the attainment of some and then stops the attainment of others. So those are things that need to be evaluated as you go forward and you're thinking about specifically what how to engage the group and how to make these things happen. And then the curriculum structure, it's again, it's based on a local property. It's an interaction between knowledge and experience packages, but this one's a little different because it's will enhance the value of, but it's almost like there's another object or another token that's going through some type of thread on this graph. And you're trying to make sure that each one of these paths that would go through this particular structural graph will provide, not only will enhance the value of, but that the token or the object that's going along that specific path has the capability of understanding the knowledge and experience package in the next step. So the curriculum structure, you start out with the basics. You don't know the basics, then you can't advance to the next level. And then, so there's a very structured way that you need to advance through these, through the structure. And if you don't go that way, then it's difficult or impossible for you to understand the material. Like you wouldn't want to start with the most advanced and go to the least advanced. So there's this idea, besides will enhance the value of, that needs to be addressed in the curriculum structure. I haven't got a real solid understanding of how to do that yet, but I think it's another area that needs a little bit more explanation, a little more development. Okay, so structure modeling, of course, identifies the system structure, and it's a good tool for actually starting to develop shared context among a group. Because if a group comes together and they really don't know their context, these are techniques you can use to start creating well-defined context. And the local and global concepts that we talked about here today were developed based on our review of the literature and working with the literature and the classic concepts. And we've established these characteristics as a mechanism to further categorize and align operational techniques and code associated with structural modeling activities. And as we go along and develop these further, we believe it will help us develop a more rigorous set of structural modeling methods and techniques. So, are there any questions?
That was very helpful. Thank you. I know you tend to go over these things again and again, and it's taking me a while to get oriented. But really appreciating what you're doing here. So one question that you have addressed before is these application structural types in contrast to the relation types of definitive, comparative, etc. So here we have. Can you go over that one more time?
Sure. Okay. So the application structural types are a higher level. So the application structural types are a higher level collection of structural modeling methods and techniques that are put together to achieve certain objectives. the delta chart, which is a decision type of process where you go through. It's a combination of a decision process and a PERT chart that Warfield put together. That is an application structural type. It is an application that's based on a number of more primitive structural types, and it's focused on a specific type of large-scale system management activity. What we did when we first started this analysis of application structural types is we went through and we sidestepped the more complex ones. And so there's a series of fairly complex application structural types that are like project management, PERT charts, network charts, those types of things that we're not addressing at this time. And what we did is we stepped through past those to the application structural types that were based on a matrix, of a binary matrix form. So we just selected those with the binary matrix form as the fundamental, foundational ones. And then we took the ones that were based on the fundamental matrix, and we mapped those to the augmented model exchange isomorphism. So that we had the matrix, the structured graphics, and the logic. We looked at those over the last few months in the enhancement structure and some of the others. And then, again, the enhanced, what was it? Matrix, right? There's a couple of concepts there that we developed about how to change from natural language to mathematics and back again. And so those are some very fundamental primary structural types.
Pardon me, but it might be helpful on page 14 of the technical report 4.
Yeah.
We have a table of application structural types, and so it would be helpful to take a look at that to know where we were with respect to that. I think Jen.
Okay, let's do that because I was doing this all from memory. So let's see, number 4, right?
Yes, number 4 and on page 14.
Yeah, I'm just trying to remember what month that was. So, do you have any idea what month that was, Mary?
Try December.
It was December.
Try. Just a guess.
12, 16. Okay, so let's try that.
No, that's the read ahead for December.
Oh, okay. So it'd be January, maybe?
Yeah,
Oh.
January.
Let me try this. Let me go ahead. I'll go to the read ahead. Number 4. Why don't I just go do that? Got that. Right, and quit doing it from memory. There we go. Page 14. There we go. Okay. So these are the application structural types, and we separated them into 2 classes, primary and compound. And then we had the class of primary matrix and primary graphic. So the curriculum structure, the intent structure, the enhancement structure, the problematique, and the priority structure were the primary matrix forms that we've been working with. the delta chart, the triply structured quad, field representation quad, the tapestry of quads, resolution structure, and uniform program planning and linked matrices, those are all compound. And so that the, does that make sense?
Yes, very helpful. So these are all, excuse me, these are all examples that Warfield worked with.
Right. So yeah, these are all out of his either Science of Generic Design or out of the Handbook of Interactive Management.
Mm-hmm.
And so take for example a quad, right? A triply structured quad that basically would use a number of the primary matrices in a hierarchy.
Right.
And then we make decisions, and then a tapestry of quads actually says, okay, now I have these quads that have they're built up with the primary matrices, and I'm going to thread my decisions through a bunch of these different quads in and out of them.
Right.
So those are very complex structures.
But they use the primary ones. Yeah.
Yeah, but they're all based on the primary ones, and then we're looking at these, we're developing these concepts so we can talk about them a little bit better. And now we're going to start assigning the algorithms, and then we're going to slowly kind of walk back through and hopefully put them back together again.
And what was the quad refers to?
It's a structure.
It's 4 elements, I presume.
Yeah. So let me again. Let's see. I have that. So it's basically. Just a second. I'll be right back.
Okay.
Okay, so yeah, we have the quad itself is in the Science of Generic Design.
Mm-hmm.
And let's see, let me find this part. But what it is a mechanism by which you address the application of structural types to basically create a decision or to have a, select some kind of problem solution. And the first level, the bottom level of the quad, which is the 4th level, right? That's your option level. So down at the option level, you'll have a collection or an aggregation of options. Oh, these are things that I can do, right? So after you've done some work to say, okay, this is my enhancement structure, and these are the problems I have, I've identified the problems, I've identified my action items, I've identified things I can do to enhance each other. Then you'd say, okay, I have some type of collection of options. And then the next level up from there is the dimension level. So then you basically, on the dimension level, you have your value system. What are my system values? What are the dimensions of that value system? And of course, those values then you use, or the dimension level you use to actually create clusters of your options. And then you use the clusters of your options combined with your dimension level and your value system to select your preferred target, what you want to do at that time. And so really it's a decision-making technical or evaluation process at quad level. So anyway.
So does the quad refer to the pyramid of 4 levels, and then there can be different kinds of quads?
Yes. So basically, he does show it as a pyramid in his 1986 IEEE work. Warfield did published the original quad work, I think in '86, and then I think Warfield and Christakis did another one, I think from the later in the 80s or in the early 90s. I forget exactly what those dates are. But the idea is that you would have in your options level, the fourth level of a quad, right? Your option, you may have used a whole series of other quads to actually select those options. So that you have multiple layers of these decision and evaluation processes. But the core piece, the core idea, the core algorithm that you go through is called the quad. First you have your options, then you have your dimensions, you cluster around those dimensions, and then you have a value system and you select the most appropriate cluster.
Great.
Or the most appropriate answer. So yeah.
That's very helpful.
Okay.
Okay, so the application structural types then, this set that Warfield worked with is, and the primary types that you have there, it's a good enough set for covering most kinds of activities, but if someone wanted to do a dissertation, they could try to do a complete taxonomy and figure that out. Thomas?
Oh. Well, this is Warfield's approach to this. These things are strongly coupled in some dimensions, loosely coupled in other dimensions, and uncoupled in other dimensions. And so this is kind of like a hardware store, right?
Right.
The application structural types is like walking into a hardware store saying, okay, well, I'm gonna build a house, okay, then I'm gonna get this kind of stuff, right? If I'm gonna build a go-kart, I'm gonna get other kinds of stuff. But these are the parts I'm gonna use.
I was wondering, it's a wonderful set to work with. I was wondering if somebody could prove that this was the only types that one could distinguish, that all the other types could be mapped onto these or something like that, have a set of
oh, well, yeah, that sounds like a mathematician.
yeah, right.
That's really good, Janet. I think that that'll be interesting. But you see, the idea of it is actually you can take these fundamental forms and you can adjust them to almost any situation.
Right.
And one of the reasons, so because of that fact, what we're trying to do is we're trying to figure out what are the fundamental characteristics that are the same and different among them.
Right.
Right.
And so that's where local and global is kind of coming out of that.
Yes, that's very helpful. And but then one could, as part of, I wish Kevin were here, but as part of the, looking across the scope of everybody who has done similar but different work, if you can identify some kind of these local, global, primary compound, that kind of, those key dimensions, then it would be really helpful for saying, where the similarities and differences lie with people who have used, the dependency structure matrices in other, with other terminology.
Right. So and I think that's really important when you start transitioning from structural modeling to behavioral modeling, and I think the only person that really started even to look at that or published very much about it at all, just briefly, was Sage. And so, because we're looking at structure here, right? And so structure first, then some type of transition where we go to this behavior modeling, the system dynamics and the DSM and all those other things that are out there. There's bunches of them, right? Where is that transition and how do you go along that? Kind of on the map, but I'll work with anybody that's interested in doing that, but it's just limited, constrained by time.
Yeah, I mean, the other thing that I was wondering is how you make determinations as to what structural type is appropriate for the particular dimension or set of variables that you're actually dealing with. And even on the VSM, for example, different kinds of structuring in different systems or different parts of the, system one. Are there particular, in VSM, are there particular structural types that are more appropriate at system one as opposed to system 5? How do you go about making appropriate selections? And I guess then at some point you're going to get onto the implications for the way the prioritization and structuring actually occurs by type, presumably.
Yeah, there's a number of things to consider there, and we're getting close to the end of our time here, so we need to wrap it up in a few minutes. But the point, those are very good comments, Peter. The idea is essentially can we do an analysis? What we're really doing here in structural modeling is working with a group to do an analysis of a structure, right? That's of complexity which the group can understand. So then, once we're trying to determine some kind of order that's there. So there's also the idea of systems that are so random that you really can apply statistics to them, right? And then there's other types of systems and problems that are very simple, like simple machines that you really don't need to use these advanced techniques on. And where the transition needs to be, I believe, one of the factors, one of the dimensions is randomness, so that we're going to be dealing with systems that are too complex for analysis, but too structured to apply random statistics. So that's kind of the next vector of switching and saying, okay, now where do we start applying the different kinds of mathematics? And so when you talk about the BSM, and so we're looking at different types of mathematics. Well, are we using statistical approaches? Or are we using analytical approaches, right? That's the first kind of big, pathway switch in the road. And I'm writing some stuff on that in another thing. So hopefully we'll get to that soon.
Thank you.
You're welcome. So with that, so anybody who has the lead for what is it going to be? The 17th.
It's a question of whether Kevin is going to be there.
Kevin and Giannis are attending a conference in Sparta, which is why they're not here. So
Right.
Okay.
Well, because I think there's still content to discuss. Biology
Okay.
report there. So it's going to be participating. Then we can continue with that.
Okay.
If he's not, then maybe Peter and I can link together to discuss.
Okay. Good. Then I'll expect you folks to figure it out and let the group know, I guess, within who's going to do what, and we'll plan on the 17th. Then.
Very good.
Okay. Thank you very much, and we'll see you on the 17th.
Thanks to all.
Thank
Have a
you.